Hello.
Hi everyone. I hope you're all doing good.
Yes, definitely.
Yeah, okay. maybe we can start putting in some energy. And so guys, are you okay? Are you okay?
Yes.
Yes. Okay. So today we came back with another great session and continue our journey in mathematics. And we're gonna talk about what today, Heini?
Our today's topic is going to be statistics. So after last week's linear algebra, this might feel a little easier and lighter to digest today. And so we're just kind of going to explore what are the methods in which we can explore the data that we have and start looking at the data sets that we have for example, to do analysis on. So just kind of those first steps of discovering what is our data like.
That sounds exciting. Yeah.
Yes.
Okay, so I guess we should start with a quick talk about what is AI42, and then we'll come back to you, Heini, and have a little more chat about what's going to happen.
Yep. So see you in a short while, Heini.
See you.
So hi again, and welcome to today's session. We are here from AI42. Hi, Håkan.
Hello again.
Yes, it is really great to see you again.
Yep.
How about chatting a bit about AI42? Maybe you can tell a bit about the motivation.
Yeah, so basically the motivation here for AI42 is we would like to give everyone here on the planet the chance to get into the interesting field of machine learning and data science. And the way that we will do this is we will have a bi-weekly stream. So every other Wednesday we will invite a speaker, a recognized speaker, or people with industry expertise who will talk about a subject related to machine learning or data science or artificial intelligence. So the way that we do is we start out here with the basics. So we learn about mathematics and statistics and probability theory. And after that, we will have a section where we focus more on languages like Python and R and Scala. And then after that, we will go more into, how do you actually do an introduction to both the machine learning and to deep learning, to MLOps, and these kind of things. And in addition, we will also have some more practical workshops where you can try out these things, the theory, into practice.
Yeah. So, yeah, go ahead.
Yeah, and the whole idea here is that you will be able to start here from scratch, and then you will be able to learn enough so that you can have a good introduction to starting your own career as a data scientist or a machine learning engineer.
That's really exciting. And if you join us at these bi-weekly sessions and join us on Instagram, Twitter, and Facebook as well, you'll have the chance to connect with the best-in-class experts from all around the world that will also come to our events and hold lectures and workshops with very rich contents. And we also try to build a close collaboration with other organizations. And we can give you the best opportunities to broaden the network in the AI and data science communities. We also want to provide more support to the less fortunate people and organizations that are not that recognized yet, even though they would deserve it. And we are in close collaboration with the global AI community, and you can see our streams at their platforms as well. And if you want to learn more, don't forget to find us on Instagram, Twitter, or Facebook. You can find our meetup page with the use of the QR code over there. And our YouTube channel, of course.
Yep. And then finally, we would also like to thank our sponsor, which is Microsoft. And we would like to thank Maida Marie, who has composed our introduction music. And all of the graphics design that you can see here on our stream is by Levente Pangor. So thank you so much to him for that.
And before we go back and talk with Heini again, let me quickly mention that in the following few, hopefully just days, we're going to make our webpage fly as well, where you can find all the content that we have shown at our sessions. And you can have some chance to practice maybe what you have learned, find some extra resources. So please stay tuned and remember to follow us.
Yes.
So, hello, Heini.
Hello.
You know, I was wondering how statistics is so important nowadays, even though maybe this field is sometimes a bit misunderstood and maybe it is not giving enough attention, not getting enough attention nowadays, even though it plays a really essential role in our everyday lives as if statistics done correctly, it allows us to extract knowledge from the complex and difficult real world. So tell us, please, a few words. Why do you think this topic is so important?
So really the topic of statistics, it actually lays the foundation for the many methods that we use in data science and machine learning as well. It is one of those topics that can seem a little dry because it goes straight into how do you calculate things. So it goes into like, if you want to find a central tendency, how do you calculate it? It might not look at how does it work so much. And I think that is why it can get a little bit less emphasis nowadays, because it can seem a little dry. And so hopefully I can help bring it to life a bit. And kind of if we look at the field of statistics, probabilities is often also included within statistics. So in these sessions, we've divided them into two. So today we can kind of focus on the basics of statistics and really laying a strong foundation before we go into the probabilities section after that.
Yeah, that sounds really cool. And maybe I would give the stage to you, but before doing so, let me quickly say that, guys, feel free to ask your questions. You can put your questions in the chat, and we're going to answer your questions after Heini is done with what she has to say. So, are we ready to have a walk in the park?
Yes.
Oh.
So good evening, everyone, and welcome on my behalf as well to our fourth mathematics session of statistics. As Eva there said, I kind of promised that this is going to be a walk in the park after last week's session when we were handling linear algebra, and kind of on the contrary, whereas linear algebra is very theoretical and abstract, and it can get a little heady and difficult to understand. Statistics, on the other hand, is very concrete, and it can really help us draw insights into our data immediately. So that is what we're going to be looking at today. And as said, we're going to be focusing on the really foundational parts of statistics today. And then next week, we're going to kind of go further into the probabilities side. So as you might remember from the previous sessions, we have been looking at our data sets here in our coordinate system. And again, today we are going to be returning to the scenario where we start with some kind of data set, and we want to start exploring that data set. And along the way, of course, we might want to start to get to a situation where we want to find that line that fits in there. And we have been kind of focusing on this question of how do we find this line? But today we're kind of going to take a step back and start with the basics of what kind of information can we draw from the data that we are working with. We might have some kind of data set that we start with, and we might need to do some kind of preliminary exploration on it before we can even think about this aspect of how do we find the line there. For example, we need to determine which variables we want to use, etc., to even consider in our problem. So just to give you a little recap of what we've been going through, we started with some basic algebra, including data sets and handling equations and solving equations. Then we went into calculus, where we covered things like derivatives and integrals. And last week, we went into linear algebra and look at how vectors and matrices are used in machine learning and how those are used to describe real-world data. And today we're going to go into statistics as the fourth lesson. And as said, we're going to have one more left after this, and that will be our final mathematics session. This is the fifth one of probabilities that will come up in 2 weeks, actually, not next week. So really, as we're going along today, again, remember all of these topics that we've been talking about, we are talking about working with data in real-world scenarios, because the data that we're gathering is trying to describe the world to us. It is trying to give us some kind of information of the things we observe around us. And so all these mathematical things that we're doing to the data, they are helping us understand that data that is describing the world to us. And that is very much what we will see with statistics today as well. So if you have not joined the previous sessions, I am Heini, and I work as a DevOps consultant in a Finnish company called Polar Squad. So I nowadays mainly work with Azure and cloud architectures and creating DevOps culture and pipelines and things like that for our customers. And I also am a Microsoft certified trainer and run Azure trainings as well. Architecture is kind of my favorite topic in that work life, but also I used to be a mathematician, and that is where my training is from. And I actually studied to become a math teacher. So it has been nice to get a chance to kind of return to my roots with this series of math lessons and really get to combine those aspects of what I do today with data in the cloud with my mathematics skills from my previous life. And so you might notice that I also do a bit of doodling with my slides here as well. So for today, we're going to be looking at statistics, and the main focus really is how can we describe the data that we have, and how can we kind of find things out about the data set that we start with. So first, we're going to be looking at some central tendencies about means, medians, and modes, and what those central tendencies can tell us and what they cannot tell us. So we really need to understand when we can use them. As the second point, we'll be looking at dispersions, and specifically at variance and standard deviation, and what those describe to us and how they give us more information about the data that we're working with. And then as the last point, second to last point, we're going to be looking at distributions of data. And then as the very last point, at covariance. So today we'll be very much at looking at the situation where you start with a data set and you need to start exploring what kind of information can you draw from that data set. So oftentimes the first things that comes to mind is central tendencies. So things like, well, I want to know the average of this data that I have available. On the mathematical side, if we look at the category of averages or central tendencies, there's actually 3 different things that we can calculate. And the first one of these is a mean. And this is the standard average that we mostly think of when we talk about averages. But there is also 2 other ones. And the second one is called a median. And the last one is called a mode. And these 3 things tell completely different things to us about our data. And depending on which ones of these we use, it will determine what kind of things can we actually tell from our data, and what kind of conclusions can we draw from that. So we're going to start with an example. So we're going to have a set of data, a very small set of data, because we're going to do the calculations by hand for the example. So a small set of data with some heights in centimeters. There kind of could represent a set of people that got measured for their heights, and then we want to just look at this data set that we've gathered and look at these central tendencies that we can find out. So if we start with a mean, this is, as I said, kind of the standard average that we think of when we talk about averages. So what that means is that we take all the heights, add them together, and divide that by the amount of numbers that we have in total. So we just take all these numbers in order and write them 150 plus 152 plus 170 and so forth. And then when we calculate, we notice that we have 7 values in this data set. So we divide that by 7, and we end up with a result of 161 centimeters. So that is our average or mean for this data set. So it just tells, just having all these measurements of heights, if we pull them all together and divide by the amount of values that we have, it will give us the mean value. And in a little bit, we're going to be looking at what are the restrictions of looking at the mean values. How does it apply to different kinds of data sets? As the second point here, we have a central tendency called a median. And a median is a little different than a mean. And what a median does, how we calculate a median is that we put our values that we have in order, and then we pick the value that is in the center. So if we first just take the numbers that we have and put them from smallest to the biggest value, so we start with 149 and we go up until 173, which is our biggest value. And then we go from both ends of the line and we count towards the center. We will then find 164 in the middle. And this is our median. So it is different than the mean. But this just means that this is the middle value from the set of data that we have. And oftentimes this is different from the mean because it is calculated differently, of course. And if we would have 2 numbers in the middle, so we would have an even number of values, then we would just take those 2 middle ones, add them together, and divide by 2. So essentially take a mean from the 2 middle values. And then the last value that we have is the mode. And what the mode is telling us, it is looking at the value that has the most repetitions. But if we look at our data set, we notice that we just have 1 value for each height. We don't have multiple values for these different heights that we have in our data set. So for this particular case, that means that we don't have a mode available there. So that is kind of the values we're able to get for this data set. So after we have kind of found the mean for our data set and the median and the mode, then the next thing that we might look at is dispersions, or the how far away is our data from our mean value. That is what the dispersions are describing, because that can give us more information. Because just if we have one particular mean, that can come from many different kinds of data sets. And we'll look at that in a little bit. How is that possible? So next, we're going to look at the dispersion for this one. So as said, the dispersion describes how far away are the values from the mean value. And we have 2 kinds of dispersions that we're going to look at. We're going to look at the variance, and we're going to look at the standard deviation. And so how the variance is calculated is that we take each of the values that we have in our data set, and we look at the distance from that value to the mean, and we square that result. So we take the value, we take the mean, and we square that result. And then after we have calculated these for all of our values that we have in our data set, then we take the mean of those square distances from the mean that we have. So if we start looking at this piece by piece, The mean value here is 161, as we calculated on our previous slide. And so if we take the very first row from our values, we take our value of 150, we minus that from 161, and then we square that. So since 150 minus 161 is minus 11, and we square that, we get 121. So that would be just one of these values, one of these results for our values. But we want to take the mean for all of the values that we have in our data sets. So that means that we're going to calculate this for all of these values in our table. So we're going to calculate it for 152, we're going to calculate it for 170, we're going to calculate it for 164, and so forth and so forth. So we're just going to go through our table and calculate all those square values of the distance from the mean. And as the next step, we need to take the mean of these values. So then we just take each of these calculated values. We start with the ones that we calculated out already. So we have 121, 81, 81, 9. And we take this, do the same thing as we did for the means for our data set itself. But now we have also this square difference from the mean for all of these values. So for the 149, 173, and 169 as well. And we take the mean. So we just take the average of this square difference from the mean for each of these values that we have. And we get 92. And that sounds like a lot in this context of, well, we have heights that are somewhere between 150 and 173 was our maximum. But we have this variance that says 92. Okay, what does this even mean? Well, actually, the value that is more often used for describing how spread out is the data is a thing called standard deviation. And the standard deviation is actually based on this variance. So it takes the square root of the variance that we just calculated. So if we just take what we ended up with there, we ended up with 92. The standard deviation would then be the square root of 92. And a lot of times that is marked with an S. Or it might also be this other kind of mark that I just lost the name for, a lambda. No, it's not a lambda. Okay. Well, you might see another kind of sign for it as well. That just went out of my head at this moment. So we just take the square root of 92, and that equals to 9.6. And this is kind of telling us the average distance from the mean for these different values that we have in our data set. So it is kind of describing how far away is our data distributed. And so when we look at these data sets, we can also represent them in a graphical form. And one way to do that is here, we're kind of going to assume that we have a little more of this height data available. So if we were to gather height data from an entire country, from the entire world even, it would actually end up looking like a distribution like this. So here, actually, let's add a little bit to our beautiful table graph here. So here, this x-axis that we have here is representing the different height values. Oops, height. And here on this y-axis, we have then the number of people. So a height is actually that will then distribute itself in this kind of beautiful type of normal distribution form, which we will also come back to at a later point. But it will kind of be quite symmetrically distributed. And in this graph, we will also have the mean in the middle. Whoops, I'm going to need my mouse there. We're going to have the mean in the middle. And then as people, so that will be kind of the average, the mean that we calculated in the previous example. If we would have a larger set over a full country or a population in a country, then of course we would get an exact mean for that population. But then of course, as we go farther into taller people far away from that mean, it will become, there will be less people that are far away from the mean, both to the shorter side and both to the taller side as well. But this value of dispersion that we were calculating as the last thing, what that is telling us is it's telling how far away from this mean are our different values distributed. So it's kind of describing to us how large is this separation from the mean to this curve. How soon does it go away from the mean? So for this particular curve, if we take another curve as an example into the same picture, and we take another curve that is a little steeper, in this case, our curve here on the outside, this one will have a larger standard deviation. So really that standard deviation is telling us how spread out are our values in our data set. And that can be really valuable information because it will allow us to not only have the mean value, but also have that information about how far away will it be distributed from our values. So we have gone through these central tendencies and dispersions, and we went through the mean, the median, and the mode in central tendencies, and then we ended up with the standard deviation in the dispersion side by looking at the variance. And so, but there are certain, let's say, drawbacks to these values because they just give us one number value out of our full data set. So what that means is that there are some restrictions and things that we need to know about these values. So if we start here with looking at the mean. So as we already saw in the previous picture, our graphs can have quite different kinds of shapes, and still they might have the same mean value. But on the other hand, we had this graph in our previous picture that was a nice bell curve like this. And here the mean would be about there. But what we need to realize is that we could have a completely different kind of data set, and it could have the same mean value. So for example, we could have a data set that goes like this, and the mean would be exactly the same. Or we could even have, let's draw a third line here. We could even have a distribution like this. And these could all have the same mean value. Of course, my drawings aren't exact, so don't take it, but we can have very different kinds of data sets, and still the mean might land in the exactly same position. So oftentimes, whenever we're working with these central tendencies of the means, medians, and modes, we do need to also look at other kind of these metrics that we can get from our data. We cannot just rely on that information because it's only giving us one number out from our full data set trying to describe it. So it's never going to be perfect. And to really kind of bring together these three central tendencies that we looked at in the beginning, if we're going to be looking at this data set here, for example, as we have the different central tendencies that we can look at. For example, we had the mean, median, and the mode. So the mode was the place where there are the most repetitions. So for example, for this distribution, it would be right there. That would be our mode. Whereas then the median is the middle value. So it is actually at a point where we draw the line, and it happens that this right side of the line and the area that is left under there equals to the left side of that line. So we're kind of able to divide the area underneath that line into half. So that is where our median would fall. The average or the mean is actually the most difficult to eyeball. So, oops. So this can go totally wrong for me, but that, for example, could be, let's see, it would probably even land somewhere in between these two values. So that would be our mean. So these different central tendencies that we have, they are telling us different things. The median is telling us the middle point of our values. The mean is just telling the average. And then the mode is telling where we have the most repetition. And so we need to consider what these values are actually telling us and keep that in mind when we're using them in finding out information about our data. And as you might have noticed, this is, of course, when we're looking at just one particular value within our data set. Of course, when we have a data set, we probably have several columns that have different information. And so in the beginning, we might, for example, start with just checking the averages and the minimums and maximum values and figuring the standard deviations just to get a general idea of what is the different data like in the different columns of our data. But then we often don't quite stop there, of course, and we kind of are looking at just each variable separately. And that is a valuable first step to just understand the kind of data that we have. And the other thing you might have noticed here is that as we were calculating the mean, we were adding all the values together and then dividing that by the amount. So if you think about it, it does not fit well for data that is descriptive and not a number value. So for example, if we have, for example, data about housing, and we have different building types. We have a, oh my gosh, these words are difficult in English. I just get them in my head in Finnish, but you know, we have apartment buildings, we have single houses, etc. We have these different house types. That is not something we can calculate means or medians with because there's no order from smaller to bigger. And there's no number values. Even if we put those values so that they're represented by numbers, still, if you were to calculate a mean, that would not give us any information at all because it is not described by numbers naturally. But for example, even with that kind of data, we are able to calculate the mode because it is telling the most number of repetitions that we can have for a specific data. So that we can do even for values that are in words, because that is just calculating the repetitions. So that's kind of what we have to consider with different kinds of data that we might have. So as we kind of were looking at our data and we were already looking at how the data might be distributed, we actually can have different types of data that we're working with. And oftentimes we are describing this with distributions. And so if we start with this situation that we were looking at in our previous slide as well, where we have, again, we have on the y-axis, we have the number of repetitions. And then, So here we have the number of repetitions. And then on the x-axis, we have whatever variable we're measuring and the values of that. And so we can have a variable that can get a continuous distribution of values for it. So what this is describing is a continuous distribution. So what that means is that as we were looking on our very first session of try to write and talk at the same time, that is not a smart idea. So even on the very first session of mathematics that we were looking at, and we were looking at number lines, the continuous distribution means that the value can get any kind of number on a number line between certain values, depending on what we're measuring. So for example, if we think about height, someone might be 172.1 centimeters, but someone else might be 172.2 centimeters. So it is a continuous distribution. There's no limit to what kind of values people's heights can take. But of course, we can decide to only look at the centimeter level. But as a measurable thing, there's no kind of inherent thing that forces it to just get certain values. So in that case, we always call it a continuous distribution. And these are all the cases where we can draw that distribution as a continuous line as well, if we want to represent it graphically. So it doesn't necessarily have to be this symmetrical, beautiful line that we have here, but it can also be any other kind of shape, but it just has to be continuous in nature. We also have a second type of distribution that is called a discrete distribution. And so this is the second type. And for discrete distribution, this is the cases where our data just gets specific values for the data. So for example, throwing a dice is a very traditional example, but it works because there's only 6 different values that can end up showing. But there can, of course, be many other kinds of values as well. And in that case, if we have a discrete distribution, we might often describe as a graphical representation. We might describe that distribution with just kind of a bar chart, where each of those values is represented by a bar. And again, the y-axis is just telling the number of repetitions. And as in our next mathematics session, we will be going into probabilities. We will notice that also the type of thing that we're measuring, whether it's discrete or it's continuous, that will affect how we calculate the probabilities as well. So this will start to tie into the probabilities side. And as we really think about it, we might be gathering some data, for example, that height data that we've been talking about in this session, and we just keep gathering that data. When we have enough data, then based on that, the data that we have, then we can start to give probabilities about how likely is it that someone will be a certain height. So when we're looking at these different values we can draw out of our data, it also ties very closely in with the probabilities as well. And that is what we will be going into in the next session of how do we calculate those values and how can we work with probabilities in the field of data science as well. In regards to distributions, there are many, many different shapes and kind of models that are in use. And Whoops. And one of the main shapes that was left out of here, for example, is this bell curve that we've been working with all throughout this session, where it is kind of this symmetrical curve where the mean can be found in the middle. And then it has a specific standard deviation that just tells how far are the values from the mean. And we can kind of find there's this specific standard shape, but then how far the values spread out from the mean, just differences. So we have specific kind of distributions that have a certain type of shape that can help us, for example, then when we're working with the probabilities, for example. So we will be coming back to this as well. So this is the normal distribution. Or sometimes it's also called a bell curve as well. So you might see that word around as well. So we've now been looking at our data from the perspective of one variable. And in a lot of cases, we actually want to look at our two variables together and how they fit together. And in that case, we often want to look at correlation. Is there some kind of correlation between variable A in our dataset and a variable B in our dataset? But when we're talking about correlation, it's really good to remember that correlation does not mean causation. And it is just kind of, even if we find that these two values are changing together, it doesn't mean that one is causing the other or the other way around. So it's just these two values are changing together. That might be what we can find in our data. So today we won't have time to go into the specific of how this is calculated, but I just want to show what the idea behind here is. So when we're looking at a correlation and for example, we're going to take our traditional data set that we have been working here, where we have our values, they seem to go together. So here on the x-axis, we have our first variable, and on the y-axis, we have a second variable. And so in this picture, it kind of looks to the eye that they're changing together. So as the values on the x-axis keep getting bigger, the values on the y-axis keep getting smaller. And there is actually a method in which we can calculate whether there is a correlation. And to do that, we use a thing called covariance. So for example, for this particular scenario, we would say that the covariance here is less than 0. And really what the covariance is looking at, it is looking at both how the variable on the x-axis, so down here we have the x-axis, how the variable on the x-axis and how the variable on the y-axis, how are they distributed around their mean. So this is actually also using the standard deviation behind the scenes. So they are kind of looking at how are they correlating with the mean, and then putting those together and looking at, are they changing together? So as the y values are going further away from the mean value, for example, higher, are the x-axis values changing in the same correlation way? So that's what it's looking at. Are they changing at the same time? So whenever it's going so that as one value is increasing, the other is decreasing, then the covariance is less than 0. But for example, if we have a different scenario where we have the values going more into this direction, so the x values are growing as the y values are growing, then the covariance is going to be larger than 0. And then as the last point, if it is just a random jumble of points, then the covariance is gonna start to get closer to 0. So there's no, we cannot find a way in which these are changing in the same manner. So what we have been looking at today is looking at how we can explore one variable that we have in our data set and looking at how we can find the different central tendencies for our data and looking at the different distribution and start to compare those with different data sets. We also looked at the distributions of data and how we can have a continuous distribution or we can have a discrete distribution depending on what kind of data we have measurements on. And then as the last point, we were looking at the correlation. And this is actually the first step that we often take in when we really want to find that line for our data set, because first we need to know whether there is any kind of correlation. And of course, in this graph, we again have just our 2 dimensions. But as we remembered with our last session with linear algebra, there can oftentimes be even more than 2 dimensions. And in that case, we will combine these methods that we use, for example, for finding the correlation with linear algebra as well. So in a lot of times when we are working with data science and going towards machine learning, we will have to combine the skills that we have learned in these different sessions. And hopefully we're gonna be able to get some exercises out for you to try on your own to see how that works. But today's point was really to just gather these very foundational skills for statistics, because next time we're gonna go into probability. And as in statistics, we're oftentimes looking at existing data and trying to find things out from that. And then as we're going into the probability-based methods that we have, then we're trying to estimate how probable is it that we will see this one value in our data, for example. So that is kind of often the next step that we then need to take. But that concludes our session for today. As I said, today it's going to be a walk in the park, a little bit lighter and easier. I hope you felt that way. And just remember, today we were doing a lot of these things manually, but a lot of times when you start to use different tools for machine learning and data science, those will have built-in features that will calculate these things for you. But it is really important that we know, for example, what are the different central tendencies actually telling us, so that we don't make the wrong kind of assumptions from it, but we can just see them as, okay, it's telling us the middle value from the data set that we have. But still we need to know, for example, how widely is the data distributed, what is the maximum value, what is the minimum value, etc. And by combining many of these methods, then we're able to draw a fuller picture of all the data that we have available. So thank you very much for today. You can find me on Twitter and shoot me with questions if anything was left unclear. I hope you enjoyed today's sessions and felt like it was a nice breezy walk. And I really hope to see you in our last session where we will be kind of bringing everything together. We will both be looking at the probability side, but also I will in the end kind of draw together how all these areas come together to really into the different areas of data science and machine learning, and how we can combine these skills that we've learned in these different sessions where we have been going these different areas through. So thank you very much, and I hope you have a wonderful evening.
Hi, Heini. Thank you. It was really cool and actually refreshing. Can you hear me, guys?
Yeah.
Oh, okay. All right. So thank you, Heini, again for your session. It was really nice today again. And yeah, it felt like having just a walk in the park. quite refreshing. So do we have some info what exactly we are going to come back and when with the next time? So,
Yes.
Håkan?
Yes. So our next session is set up for 2 weeks from now. So that's March 10. And then Heini will continue with the last session on mathematics, which will be on probability theory.
So nice. That's really exciting. And Heini is actually, yeah?
We got some comments here from the audience.
Yes.
Got a comment from Istvans. He said, "Thank you. This was indeed way more simple to follow. I'm looking forward for the next one."
Yes. Thank you, Istvan, for your nice comment. And I can't wait to see you at the next session as well. We got some answers from the audience. I know, for example, we have a few people who are always coming back and following our lectures. So that's pretty cool. And wow, it was again a great time to walk through on some mathematics again. It's always really cool to refresh these things in our head. And I think it's even for those who are working with these every day, it's really nice to go back sometimes and walk through on these once again. And yeah, so thanks, Heini, again.
You're welcome. I don't know what you saw, but I got stuck into some kind of loop and not connecting. But I'm not sure if you saw me here making nice facial expressions at the laptop.
Yeah, I seen that something happened, and it was funny. I was trying to talk to you and asking questions from you, and you were just looking at me like that. And I'm like,
oh yeah,
okay. Yeah, so thank you again, everyone, for joining us, and we are going to see you on the 10th of March.
Yes.
Am I correct? Right? Yes, at 5 o'clock in the afternoon, where we are going to show some cool stuff about probability. That's my other favorite sessions, I think, because
that's kind
it's also really exciting as well. Yeah, so can't wait.
Yeah.
Me neither.
Yeah, so with that said, thank you so much to Heini, and thank you so much to everyone who's been tuning in, and to everyone who's looking at this afterwards on our YouTube channel. And looking forward to seeing you on March 10. Thank you.
Bye.
Thank you. Bye-bye.